Shankar,
Ma'am,
can you start, Shankar?
ma'am, shall we start, ma'am? Start பண்ணலாம், ma'am.
Okay.
Okay.
Good morning, all of you. On behalf of Department of Civil Engineering, Dr.N.G.P Institute of Technology, I welcome you all for this online webinar on numerical modeling. In association with the Builders Association of India, Coimbatore Center, we are organizing this webinar. I welcome our today's chief guest, Engineer Er.Praveenkhanna Udayakumar, Senior Engineer, Arcadis, Bangalore, to deliver a webinar on numerical modeling. We are very happy to have Engineer Er.Praveenkhanna as our chief guest today. Thank you for accepting our invitation, Er.Praveenkhanna.
Thank you, ma'am.
I welcome all the participants for this webinar on numerical modeling. Now I invite Mr. Shankar, coordinator of the program, to introduce the guest to the participants. Thank you.
Thank you, ma'am. Morning, all the participants. It gives me an immense pleasure to introduce our today's chief guest, Engineer Er.Praveenkhanna Udayakumar. Engineer Er.Praveenkhanna Udayakumar is currently working as a senior engineer in Arcadis, Bangalore, and he has over 9 years of experience in both the consultancies and the research experience in spectral wave modeling using Mike 21 model and SWAN, understanding a wave transformation and other coastal process using numerical modeling. Praveenkhanna completed his bachelor's in civil engineering from Sri Krishna College of Technology, Coimbatore, and MTech in coastal management from Anna University, Chennai. He also has experience in oceanographic field surveying, including deployment and retrieval of tidal gauges, current meter, OBS, and a droplet velocity instrument. Apart from that, his experience including hydrology and water conservation studies, shoreline management, oil spill modeling and management planning in air pollution dispersion modeling and land use studies, soil wage management, noise pollution modeling, and shoreline changes studies. He also studied environmental impact assessment for different sectors such as ports and harbor, thermal power plants, highways, and oceanographic climatic research. His software proficiency include Mike 21, Mike 3, and SWAN, and ArcGIS, NV, and AutoCAD. In an extreme talent person, it take an immense pleasure in welcome you, sir. We welcome for the program.
Thank you. Thank you, Shankar. Thank you, Muthapriya, ma'am. Can I present my screen? Am I audible to everyone?
Yes, sir. It's audible, sir. Now you can present.
Yeah. Let me know once you can see my screen.
Yes, sir. Screen visible, sir.
Okay, thank you. Thanks for the introduction, Shankar. I am Er.Praveenkhanna. I'm working as a senior engineer in Arcadis. Before going to my presentation, I thought I'll give you a brief introduction about myself, and we'll jump into the presentation. Before that, I'll just show you what we are going to have in this entire presentation. So I will have my self introduction, then I'll give you a brief on the types of modeling we have, then why or what is mathematical modeling and how we typically use mathematical models. Then we'll see how environmental modeling can be used as a tool for management. Then we'll see different numerical methods. Then as you know from the introduction, I am more into coastal modeling, but as the name suggests, it is to introduce something new to the participants. So I thought I'll include something about computational fluid dynamics. Computational fluid dynamics is a kind of modeling technique. Here I am not including my coastal experience. Because if you see coastal engineering will require modeling, and there are some certain tools that can be used for coastal modeling, like Mike 21, Death 3D, all that. But this computational fluid dynamics is something which even the industries haven't used for the civil engineering purpose. Most of these tools are used for mechanical and understanding aeronautical sciences. But here I'll give you a brief on the projects I have worked with the tool, and what kind of projects we have handled. Then we'll see if you have any questions, we can discuss on that at the end. And moving to the introduction, I have completed my bachelor's in 2010 and the master's in 2012. I have been with 3 different organizations before Arcadis, and I have 9+ years of experience so far. My experience can be classified like project management, strategic planning, quality control, quality auditing, then coastal hydrodynamic studies, then computational fluid dynamics, environmental impact, coastal research, fire and evacuation, then corporate social responsibility, then understanding air, groundwater, marine, beach sediment, and soil environment, then construction site monitoring as well. I'm proud to say that I'm certified PMP. It's a prestigious one from the US, and I hold dual chartership from the Engineering Council UK. Then I'm internal auditor, quality auditor. I'm a certified internal quality auditor, which is issued by British Standards Institute. Then what are the types of modeling we have? Why they do modeling? Before going to before understanding the types of modeling, we should know why they use models, why they use modeling techniques in our real life scenarios. So modeling can be defined as fundamental knowledge or experience to simulate real life condition. So why we have to simulate something like that is to understand the system. Like for example, we can consider a structural analysis system, and why we can analyze that is to understand how the joints work, how the load is distributed, right? It is the same way we use modeling to be cost effective. Like we can't build an entire structure in this, right? So to be cost effective, then modeling is an efficient tool whenever uh, uh, in real case you can't do it. So you analyze everything using models, and the entire system, entire nature is very complex. So in real life condition, anything could happen. So if you wanted to test it prior, you have to do a modeling study. So in broad sense, they use modeling techniques for uh, two reasons. One is research oriented, which is long term, which may not have a solution. You keep researching and see how changes occurs. And management oriented is like something you have with a fixed solution, like immediate solution you'll give. For example, the structural analysis thing. So what are the types of modeling we have? As physical modeling, empirical modeling, mathematical modeling. The physical modeling is nothing but building a miniature of a bigger structure. Same building, you can make a miniature and give real life conditions and test it. Empirical modeling is nothing but a statistical analysis. It is mostly data based. Like it may not give you an exact result, it will give you something close to reality. So what they do is they'll observe data for a long time. They'll see how it works. They'll find patterns. They'll relate it to the current situation. That is how empirical modeling works. But mathematical modeling, how it works is like using theoretical formulas. Here they use fundamental theories and governing principles, and to derive mathematical relationship between the variables known to, like variables which have significance in building the model. So this mathematical modeling, uh, how it emerged is like people couldn't uh, model the entire reality, right? It was having very too many physical limitations, and uh, we were in a need to find empirical relationships to solve difficult conditions. Then mathematical modeling, what it does is it will create values or variables. It will find variables from the real life condition. It will assign to some kind of similar symbols and equations. So uh, we'll use the equations are already derived. It is already existing. Nowadays what we are doing is just put the variables in the equations and run the simulation. And uh, as it is mentioned, we use mathematical calculi, and it already had a well-defined meaning, and it is approved by different societies. And we are using the same concepts and the same formulas for now too. And uh, so theoretical concepts and process fundamentals are used to derive equation that establish relationship between system variables. System variable is nothing but the existing nature. Then based on the variables, we'll just input different values to the variables. We'll use different equations based on the condition. We'll solve the unknown result. Before we had computers, it was done manually, and most of the manual work were carried out for a small closed uh, conditions. But this was done because manually we were not able to uh, simulate or calculate complex and dynamic systems. Now, after we got computational tools, we are using complex systems in computer, and we could solve any kind of modeling, mathematical modeling using computers now. And typical use of mathematical models, we can classify the mathematical model into two categories mainly. One is deterministic, one is probabilistic. Probabilistic will give you probabilistic or statistical relation. Like they can just say, for example, this weather reports are more like probabilistic. They can they can say if it will rain or not based on previous scenarios. Previous scenarios is in the sense they will study the condition for 100 years and see how it will be tomorrow. So that's how it will be if you see in reality, it may rain today or it may not rain today, but some kind of information you can get from probabilistic, which may not be same as realistic. But deterministic models are more of a realistic one. They are again classified as continuous and discrete. Continuous models are used for static and dynamic conditions. Statics are like a simple algebraic equation they use. It could be one algebraic equation or a system of algebraic equations. But dynamic one is using ordinary differential equation, partial differential equation, or difference equation. Uh, Overall output, what we get is more like a linear or non-linear results, which can be differentiated as analytical or numerical. And so environmental modeling, a tool for management, how we can use different tools or different equations for the management purpose is first we have to understand the concerns or the issues we come across in each of the environmental media. Like we can classify the environmental media into five different environment: atmosphere, surface water, groundwater, subsurface, and ocean. So atmospheric modeling is more like air, gases, and which is above the land, and surface water is on the surface, like lakes, rivers, all that. Then groundwater is which is under the ground. And subsurface applications include man-made issues like leachate and some solid waste issues, all that. Then ocean, obviously, like the modeling of sea, hydrodynamics, all that. So first we have to find the issues or concerns, like what kind of modeling. Yeah, before moving to the model, you should understand what kind of problem you wanted to solve. Like if it is atmosphere, it could be hazardous air pollution. You can model air emissions, then toxic release or acid rain as well. And then particulates, smogs, CFCs in the atmosphere. Then you can also understand the health concerns, how the atmosphere is directly influencing health. And then moving to surface water, you can understand wastewater treatment plant discharges to lakes, rivers, then agricultural runoffs, stormwater discharges, potable water sources, and availability. Then food chain, how it transfers from one place to different places through rivers, all that. Then groundwater, you can again see leachates infiltrating groundwater, then groundwater leakages, then how it will help in agriculture, how much water sources available underground, all that, how much injection is required. So this you can understand from modeling related using modeling related tools. Then subsurface, what they use it for, mostly like leachates, solid waste and hazard waste disposal sites. They usually dump underground, and they'll not model how the leachates spread across aquifers, and it will impact. And ocean, what they do is like in if you see relation to pollution, they'll see sludge disposal, spills, outfalls, and food chain. But it is not restricted to this. You can understand hydrodynamics, how ocean is influencing weather, then how waves are eroding the um, land area, like coastal area, and how sediment transport is happening. So whatever is presented here, it is more like environmental management tool, and more like human interventions. But there are many more natural interventions also could be studied through modeling. uh, and what you get from models, like what kind of results you can expect from each of this modeling is like, if you are modeling atmosphere, you can understand concentration profiles, exposure, design and analysis of control process and equipments, evaluation of management action. You can see how it is working. If already management actions were taken, how it is performing. In compliance with regulations, how it is complying, the actual condition, how it is matching with government regulations, all that you can see. Then moving to surface water, you can see the transport of pollutants, concentration of plumes, how it is dispersing. Then design, again, you can use it for understanding control process and equipments, waste load allocations, evaluation of management action. So the results will be more or like similar to each other, but if you see the maximum usage of these tools are for the compliance purpose. Most of the industries, they do modeling to understand how they comply with the regulations and what kind of improvements they can do to uh, reduce their pollution or improve their system. And what are the numerical methods we use? This you might be knowing. Finite element method, you use it for structural analysis mostly. It is just connected through elements and nodes, and nodes will be having some formulas where it will distribute the formula to other nodes through the elements. So it will use partial differential equations, and it will approximate different uh, 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 variables, and it will transfer it from one node to other. So that's how finite element method works. Then spectral method, how it works is more similar to finite element method, but the difference is they use fast Fourier transformation. The equations only differ, but uh, the method remains same. And the finite volume method, what it does is it will divide the entire volume or the atmosphere into different boxes. It could be a square, a tetrahedral, or a cone, whatever it is. It will divide into smaller boxes. The formulas are applied to the sides of the boxes. So it will solve the formula for one box, then it will transfer it to the next one. So that's how finite volume method works. And finite difference method, it approximate differential equation. And this is a method it use most of the partial differential equations in the modeling. And these methods are used to approximate the solution of governing differential equation in the mathematical model by dissecting the domain into mesh grids or smaller objects. So whatever the cases, whatever the numerical methods are there, they what they does is they'll divide the bigger equation to smaller elements, nodes, or mesh. Then they'll solve the problem. So instead of solving a bigger problem, it will solve small boxes. It will accumulate everything together and show it to as a overall result. So what happens is the errors will not be that much if you compare it with the statistical analysis, but still there will be losses transfer while transferring from one element to other, or one mesh grid to other, or one volume to other. So other than that, this method is more accurate than statistical method or probabilistic method. And before moving to computational fluid dynamics, is there any questions from you guys?
Sir, sorry for interference. Just hide the dialog box, sir.
Oh, sorry.
Okay. Sir.
Yeah. Anything else?
Nothing, sir.
Okay. If no questions, we'll just move with other slides. So what is computational fluid dynamics? It's a branch of fluid mechanics, uses numerical analysis and data structure to analyze and solve fluid related problems. So what mechanical industry they use this tool for is more to understand fluids. any material, they'll convert it to fluid, and they'll understand how it works and what kind of results they can expect. So it is used by many industries in their development work to analyze, optimize, and verify the performance of design before costly prototypes or physical tests are done. So this is the purpose. Then what we use in Arcadis is Flow 3D, a highly accurate CFD software tool that specializes in solving transient and free surface problems. And it is working like based on structured finite difference and control volume measures for fluid and thermal solution. I'm just presenting everything related to fluids, as my projects are more related to fluids and not mechanical or air. Air studies also there, but again we'll convert them into fluids, and whatever we carry out will be doing it as a fluid volume. And this Flow 3D works like a finite element mesh in Cartesian and cylindrical coordinates, and it will carry out structural analysis. So it will use here Flow 3D works in two different ways. Whatever physical structures are there, it will convert them into finite element measures, and whatever the open volume is there, like if you are putting fluid inside a pipeline, the pipeline will be considered as a finite element mesh, and the water will be considered as a final difference or control volume measure. So here whatever we carry out only for the fluid, and it will consider the outer structure as a solid. It will not test the solid because our focus is to understand flow and water related problems. There are many tools where you can understand the structural impacts as well, because of, for example, if you want to hold some water in a pot, in Flow 3D, you can understand only the water inside the pot, and you can't model the structural part, the pot itself. But there are tools where you can model the pot as well, how much pressure the water is exerting, how much deformation is happening in the structure. And in Arcadis, we use different commercial and open source tools. Flow 3D is one of that. We use ANSYS Fluent or CFX, then we use Star CCM, and any of the software tools require CAD modeling tool, that is, but we are using Rhino 3D, not AutoCAD. Rhino 3D is an efficient tool for building structures, which we can use it for safety purpose. Then we also use open source tools, like we use Fire Dynamic Simulator for understanding fire evacuation, fire spread modeling, all that. And we can use, we are using OpenFOAM for smaller projects, because the complexity for using open source are more, and you may have to use a lot of assumptions in open source tools, but commercial tools will give you more accurate and better results in a shorter duration. And these are some of the flagship projects. For example, if you consider flow diversion study, we have done more than 10 or 20 projects under flow diversion study, but whatever mentioned here are just flagship, which are like a major one. And as I told, computational fluid dynamics could be used for different field of research, and what we are doing in Arcadis, like we are focusing on only three different parts of modeling. One is hydraulic modeling, then heat and mass transfer modeling, then reaction engineering. So whatever I'm presenting here in this for today's discussion, doesn't include any of the coastal problems. So coastal is a separate division. You use different kind of numerical methods and tools. But computational fluid dynamics, as I told, it is a niche field for fluid modeling. So I'm presenting only the projects which we used computational fluid dynamics tool and the related projects. And for hydraulic modeling, as I told, first you have to understand the problems or issues or concerns. So the concerns, different concerns we received from our clients are like flow diversion. The client wanted us to see how diversion could impact or what kind of system, how much minimal system is required for diversion, all that. Then it could be like velocity distribution and analysis issues. Then dispersion issues, like there is no enough dispersion in the fluid. Then mixing studies, how efficiently it is mixing. And sedimentation analysis. If there is a pipeline with solid particles, how the sedimentation occurs in the pipe. Then river and flood modeling, how safety could be used for river and flood modeling as well, like dam break, all that. We try to understand how the one presented here will show you how the spillway reservoir spillway is working. Then moving to heat and mass transfer, we did thermal analysis, internal airflow dynamics, then external flow dynamics, then fire and evacuation, how fire could happen, where fire could happen, and how much time it will take to evacuate people from the disaster place. Then reaction engineering, it can model multi-phase flows, multi flow with the different densities or multiple phases, like water, air, water, vapor, and solid ice. And reactive flows we can see. Then surface chemistry also, you can understand um, how the reaction between liquids, fluids, or gases are happening. And moving to the project, the first one is the Beaver Creek project. We did this for North American Arcadis. And here they just wanted to understand the free surface flow, like how the velocity is distributed along the entire channel. So if you see, if you follow my mouse, this is the basic inlet from the creek. The river water goes into this to the water treatment plant on the bottom here. So the flow is like this. It flows. It follows the long tunnel, and it comes to the weir. It will flow from the weir to the water treatment flow plant. So here the client wanted to understand how the velocity is distributed along this the entire stretch of their construction. So whatever I'm presenting here in this today's discussion are something like an initial condition. So before modeling, what we do, like we'll simulate the actual condition, whatever the client give us. Like for example, client will say there is a pipeline for 100 meters, and there is this much velocity at the inlet, and this much velocity at the outlet. So this is the initial condition we'll simulate at first. We'll see if it is working as they are saying, and then we'll modify the conditions. We'll see if we can add more pipes to the system, or how we can improvise the entire system. So whatever I'm presenting, it is like initial conditions only. I'm not presenting final results of the project, but it will give you a pretty good idea about what the project expectations are and how we are carrying out. And even you can relate it to your project work if you students are working on something, and you can use such modeling tools for your work as well. And it is pretty simple. They wanted to understand, there are diversions at the end. They just wanted to understand if the velocity is equally distributed, if the water is reaching this image may look very small, but in reality it is a very a longer stretch. And uh, they'll see first they'll see if the water is reaching properly without any problem. It is reaching till the water treatment plant, or if there is a hydraulic jump, and if there is erosion possibilities, what kind of solutions we can give. All that they'll try to understand just with this velocity modeling. Then moving to uh, uh, another kind of flow diversion study, it is a splitter box study. If you see, this is the inlet, which is 32 CFS, and these are the three outlets. There is another outlet on the right side, but it is closed now in initial condition. But the client requirement was to understand how efficiently we can distribute. Like if you see, it is 9.3, 9.54, and 13.65 CFS in each outlets, but client wanted equal in all the three. To make it equal, what kind of modifications we can do? That is the study, and we try to make different uh, uh, wear changes, gate arrangements. We included baffles. We modified water inlet velocities. So making different changes, simulating different conditions, we achieved equal distribution on the outlet pipes. So this is the about this study. Again, this project is for the North American Arcadis. And the third one is dispersion modeling. It's a chlorine treatment plant, chemical contact tank actually. This is the inlets are here. The inlets are only here. There is no inlet anywhere. And the outlet is a gate here, a wall. You can say it as a weir as well. So water will be overflowing from the tank. There is another tank here. So this is the initial condition how the chemicals are dispersing inside the contact tank. If you see, these are the baffles. These are the small baffles they have, and in the first section of this tank, there is a baffle with bottom opening. So if you can see, there is spread across these baffles as well. So the purpose of this uh, project is to modify baffles and see how efficiently we can disperse the chemical across the contact tank, and we can efficiently use the tank for the desired purpose. So if you see, we can based on the velocity here and the outlet velocity, we can understand how much is the flush ratio. Like for any box with certain inlet and outlet condition, there will be a flush ratio in which the entire water in the system will be drained out. So we'll understand based on the flush ratio. We'll fix up the timing. We'll calculate the flush ratio, and we'll see how the dispersion is happening inside. And moving to this, the next project, it is to understand sedimentation. It's like wastewater treatment plant, the tank which glows, the pipe which leads to the wastewater treatment plant. There is screens here. Client wanted to understand how efficiently we can trap all the sediments or particulates. The first scenario was very um, with various approximations, and we have considered only plastic particles. With plastic particles with certain density, we modeled it, and most of the particles are trapped inside the first tank, where so that there were no requirement for modification of this screens or vias present in this junction. But in reality, it is not restricted to um, plastic. There will be solid waste, there will be sediment, which has higher density as well. So we simulated different scenarios with the different density particles. We saw how much it is getting trapped here and how much we are getting to the tank, how big the screen should be, how we can position the screens for effective um, trapping of waste. So all this we have tried modeling, uh, and these all these projects are completed, and we have presented the results to the clients. And moving to next project, it's to understand the reservoir spillway functions. So client wanted us to understand if the spillway can hold water at different scenarios, like maximum flood and 1,000 years, 100 years, 10,000 years, 150 years flooding condition. We model the, like, whatever the different elevation condition. We'll see if the spillway is working with lesser fluid number, to understand if the flow is supercritical, subcritical. So why we understand this is to understand the erosion pattern. If hydraulic jump is happening, then the erosion will be more along the channel. How we can protect the banks, all that we have to see. So the model was pretty simple, but there were more conditions or variables that has to be considered. And whatever the animation you are seeing here is depth averaged velocity, uh, and the fluid number will be like uh, in relation with the velocity. And uh, we modified different spillway condition, the finger wear heights, the gates were uh, added to the wear. So different scenarios we have simulated for different flood conditions, and we have given them the expected results. And this one is for Middle East, Abu Dhabi. And the project looks very simple. What is happening here is client wanted us to understand the dispersion of chlorine in water tank. Before sending it to the public, there is a water tank, there is a dispersion inlet, chlorine inlet, water inlet separately. But in reality, what they are doing it currently is they are just adding chlorine with the inlet water pipe. So whatever flow it is coming inside, it spreads like this. We have specific flush ratio, as I told. In certain number of in certain time period, the dispersion should happen in the entire tank. And we try to model and see the initial condition, and we found there are more shadow areas where the dispersion is not happening. So in different scenarios, we simulated with a different inlet of chlorine inlet location. We modified inlet location and saw how it disperses, and how we can efficiently use the stack. And moving to next project, It's related to temperature and thermal analysis. Client wanted to understand efficiency of air air system, like AC system, AC circulation system. If you see, it's a double deck um, building. And the ground floor has the air inlets on the top, and on the first floor, the air inlets are at the floor. So yeah, we try to see how it performs. The current condition is performing. Then we made a different modification to the system. We modified, like changed it to bottom, changed it to top, all that. We have simulated different conditions, and we saw how efficiently we can spread the AC cooling system to the entire building. And this one is to understand how the building is performing in line with the regulation of Hong Kong. Hong Kong has very good environmental regulation, and if you see, the regulation says the pedestrians should have certain number of certain velocity of air to be there present in the system. So the pink buildings you see here are the one the client is developing, and orange buildings are already existing. We initially did some wind analysis. We found predominant wind direction. We gave in this picture, you can see the north west wind, and we saw how the alignment of building is impacting the pedestrian air circulation, and based on our results, client has modified the alignments of this building. We simulated different alignment scenarios. Then we saw how efficiently the pedestrians are getting the required regulation mentioned air circulation. So that is what we did here. And this project is to understand jet fire. Like there is a pipeline, fuel pipeline or petrol, gas, like that. There was an outlet safety provisions. Client wanted to understand if the safety provision works in case of fracture in the pipeline, and if there is a fire, how much spread it will take, how long the fire protection will work, and how much time they'll have to evacuate to the place, how much time they will have to modify the entire system. So we did different scenarios and understood how the fire is spreading. And for this project, we used a fire dynamic simulator, which is an open source, and the project is for UK. And this is for one of the client, Grace Davison. They are more into chemicals, and this one is a cyclone chamber. Air will be coming from here. The polluted air will be filtered in this cyclone chamber. It's like based on gravity and magnetic separation. So the polluted air will go into the cyclone, exit in this top top outlet, and we try to understand how much pollution is being controlled because of the cyclone and how efficient it is. And we also did some projects to understand impeller blades, how it performs, how much big the impeller blade should be to for a better mixing. So this is a mixing tank with a smaller blade, bigger blade, how it performs. and what kind of modifications we can do to the blade to make the mixing effect. And this is one of the last slide of today's discussion. It's more of reaction engineering. The client is developing this rescue chamber, which will be placed inside mine. Like during disaster, the mine will be collapsed, and people will be inside this rescue chamber until the rescue team comes and saves them. So, as you know, when we breathe out carbon dioxide as well. So these are the curtains they developed, carbon dioxide absorbing curtains. So we model different scenarios to understand how much of the carbon dioxide reacts with the absorbent curtains, and how much time they will have to rescue these people. So this is one of the project we did for reaction engineering. Any questions, guys?
Thank you, sir.
Thank you.
So there is a few questions in chat box.
Okay.
So can I read that, sir?
I'll see the.
Oh, okay.
Okay, we'll start from. Regression analysis comes under statistical modeling. To answer Shashwata, and as there are three different types of modeling. Can these each model be used for validation of results obtained from other two models? Yes, we can do it, but uh, it will not be matching with the mathematical modeling, because, as I told, they are like far from the reality. They follow the pattern. Just the results are based on the pattern, nothing but the data-driven approach. So you can use it, but you can't present it uh, as a good comparison. You have to do a real life or realistic data analysis, or you have to go to the site and measure real life data condition, or you have to collect data in real life to compare it with the results. Then just comparing with other two modeling results. That is not the wise way, but still you can do. If you just wanted to um, uh, relate it in, if you are not worried about the result, you just wanted to find a relationship, then yes, you can compare it with other models. But if you are doing mathematical model, and if you are expecting some results, then you have to go collect data from site, and you have to compare it, validate it. And the flush ratio is nothing but uh, see, if you consider a tank, there will be inlet, there will be outlet. So, the water in the tank will stay certain time, right? After, based on the inlet and outlet, this old water will go through the outlet. So, how much time it takes for the old water to go through outlet is called flush ratio. And fire sense simulator, it's a fire dynamic simulator. It's a open source tool. Yes, you can. They have a commercial version also, which is more user friendly, but the free tool always will be little difficult to use it. Yeah, any experiment you should use it. So what we do is we create a model, any model will not give exact result in the first time because we are using empirical formulas. Okay, so for training this model, we use different calibration techniques. We'll use different constants. We'll input different variables into the system to fix the initial condition. So once the initial condition is set, you can validate. If you don't have, if you don't need validation, also fine. But if you want some results, you should validate it. But initial only if you run the initial condition, if you set up the initial model perfectly, you will know if the validation is required or not. Validation is nothing but a second check. Like you are doing a second level check of what the model is giving. Sometimes you can do validation, sometimes you can't do validation of the result. But the CFD tools are most widely accepted, and the results of this tools are more reliable. So sometimes in diversion studies and all, you can't do the model validation like immediately. Maybe after developing the diversion structure, once the velocity of water is stable, then they can validate and see if the system is working. But it will work. In rescue chamber, what kind of material? Uh, this I am not sure about the reaction engineering part. It's not reusable, but it's not reusable. The model we carried out, where we didn't carry out the reaction part. We just modeled how much time carbon dioxide is accumulating in the system. If you see the presentation, it will show the graph of how carbon dioxide is accumulating. In the model, we didn't carry out CO2 absorbent because they had patent issues. They can't share the absorbent real nature. So once we give the time, how much time the carbon dioxide accumulates, they will do the reaction engineering. But it can be done with the model, but client didn't expect us to do the reaction part as well. Can CFD be used for soil seepage in the sense leachate? If it is leachate, yes. Soil seepage, if you are asking about water and water seepage can be done, but not with CFD. There are different groundwater modeling tools. So you can use those for seepage modeling. And any more questions? Did I answer everyone, like everyone's question? If you have, if I'm not clear, I can answer it again. Okay, if everything is fine, ma'am.
Thank you,
Thank you,
Praveenkhanna.
ma'am.
We had a very nice session and informative session, and we have got very good feedback through chat
Thank
box.
you.
Participants, if you have any queries, you please post in chat box. Gust is ready to answer.
Yeah.
Thank you, Praveenkhanna, for accepting our invitation and delivering the
Thank you,
session.
ma'am. Thank you so much for the opportunity. And I thought CFD, most of the people here are even industry expert, doesn't know much about CFD and how it can be used for resolving fluid related issues or problems. It will be a good start for everyone, students. If it is, you can use it for your project. You can see how it works. There is a lot of scope for CFD in industry now, and you can use it. It's a niche field for now. Yeah.
Praveen, dear Praveenkhanna, few participants asking for your contact details.
Yes, ma'am,
Can
you
you
can share.
share
You
your
can share it.
email ID?
Yeah, you can
Yeah,
share it.
you okay. Your email ID we will post.
Yeah.
Okay.
Thank you so much.
Participants, if you have any queries, you please ask. Otherwise, we can close. We will send the feedback link through chat box.
Thank you, everyone. Bye.
Thank you, Praveen Khanna, for your valuable time and informative session.
Thanks again,
Um,
ma'am.
Shankar,
Ma'am.
Shankar, you please propose vote of thanks and close this session.
Okay, ma'am. Okay. I deem it a great honor to propose a vote of thanks on this memorial occasion. On your behalf, Department of Civil Engineering, Dr.N.G.P Institute of Technology, Coimbatore, I thank our resource person, Engineer Praveenkhanna Udayakumar, a senior engineer of Arcadis, Bangalore, for gracing this occasion with their presence and sharing their valuable thoughts. We are forever grateful to our chairman and secretary, ma'am, for their guidance and support in all the effort. I hold full thanks to our principal for their encouragement and support in conducting an event. I extend my thanks to our head of the department, Dr. Muthupriya ma'am, for their continuous supports and guidance in organizing this webinar. I would like to thank all the faculty members for their contribution and variable suggestion. I thank all the participants present here for your cooperation in making this event great success. Thank you, participant. Thank you, ma'am. Thank you, Mr. Resource Person, Engineer Praveenkhanna sir. Thank you all of all.
Praveen,
Ma'am?
can you please post your email ID?
Yes, yes, I'll do that, ma'am.
Okay.
I did, ma'am. Thank you.
Thank you, sir. Ma'am, shall we close, ma'am?
Shankar, let us take a few 5 minutes. Participants can fill their feedback. Then we close.
Ah, okay, ma'am.